let's do some more stuff. We got some more formulas. Now, these are ones you don't need to memorize. They'll be provided for you on a sheet. They're the sum and difference formulas for, I think, obvious reasons, but they tell us how to evaluate trig functions of a sum or a difference of angles in terms of the values just on those individual angles. So, for example, sine of alpha plus beta, we can compute it just knowing sine and cosine of the individual alpha and beta, right? And that could get us the sine of just the sum itself. So we have these formulas for sine, cosine, and tangent. Let's do a quick example. This is not a prove, an identity problem, so maybe it'd be nice to take a little break from that. But they give us some information about sine of alpha and sine of beta. And we want to find cosine of alpha plus beta. So they're asking us to find cosine of alpha plus beta. So that means we're going to need to use this identity here. And I'm just going to start, I guess, by writing it out. Cosine alpha, cosine beta, minus sine alpha, sine beta. Now they gave us the values for sine alpha and sine beta. They did not give us the values for cosine alpha and cosine beta, though. We need to find those. That'll be a little bit of side work. So let's work with the alpha function first, or the alpha angle first. Let's find cosine alpha. And we'll note that all they did was they told us that sine alpha is 5 over 13. It's in the first quadrant. So if sine of alpha is 5 over 13, then I can make a little right triangle with alpha as the angle. And I can label the sides in such a way that will agree with that statement. If sine alpha is 5 over 13, that means that the opposite side has to be 5 and the hypotenuse has to be 13. That SOHCAHTOA tells me how I need to label it. If I want cosine of alpha, what I really need is the adjacent side. What do? Pythagoras. All right. So I'll call this side x. Pythagoras tells us that x squared plus 5 squared is equal to 13 squared. And so x squared is 13 squared minus 5 squared. 169 minus 25. Oh, 144. And so, square root and all that. We get x is 12. We know it's going to be a positive 12 because they told us that alpha was in the first quadrant, so both the sides will be positive. So that means we know that cosine alpha is equal to 12 over 13. Awesome. We have that value. The only other value left to find before we're ready to plug stuff into this identity is cosine beta. We can do something similar for that. We can still draw a right triangle to help us find it. We're just going to have to make the correct adjustments for sines. They told us that beta is in the third quadrant, so we know cosine in the third quadrant is negative. So they told us that sine was negative 3 over 5. And we can find x doing the same thing, right? X squared, just using Pythagoras, is 3 squared plus 5. Whoops. Let me do this correctly. X squared plus 3 squared is equal to 5 squared. Guess what x is?
4.
Yeah, it's a nice 3, 4, 5 triangle, right? So what is cosine of beta? Keep in mind that beta is in the third quadrant. Negative 4 over 5, yeah. So we've got all the pieces we need now. Now we can go back up and say, oh yeah, what were we doing? We wanted to find cosine of alpha plus beta. So cosine alpha was 12 over 13. Cosine beta was negative 4 over 5. Minus sine alpha is 5 over 13. And sine beta is negative 3 over 5. So all we need to do is simplify this, a little bit of arithmetic. Let's see, minus 48 over 65. This will be a plus 15 over 65, which is a negative something, 33 over 65. There's one or two practice exercises like this, and you should get your result in terms of a reduced fraction, and as opposed to a decimal. And actually, one of the problems says, and I don't remember what it says verbatim, but it's something like this: like use a sum or difference formula to find cosine of 15 degrees. And what they're getting at there is for you to note that 15 is the same as 60 minus 45, right? So you could use a difference formula with those values, and then you want to use the unit circle to grab those values. What you don't want to do is just throw in 15 degrees in the calculator and write it as a decimal. You want to get an exact value using that identity. Okay. Questions on that example? All right, so that was kind of a nice, fun computational one, a little diversion, right? It's not all hard work, you guys. Some problems are just for fun. Now we're going to show that, it's another prove, that sine of 180 plus x is equal to negative sine x. So aside from the fact that this this problem is in this section on sum and difference formulas, I might be, have the inclination to check out the sum and difference formulas just because I do have a sum inside this sine function. So if we look back up here, I think it's the first one. Yeah. So sine of alpha plus beta is equal to sine alpha cosine beta. I'm just going to write it out. Sine of alpha plus beta is equal to sine alpha cosine beta plus cosine alpha sine beta. So we're going to use this to help us out. Sine of 180 degrees plus x. So what should the expression on the right side look like if we're using the sum formula for the sine function? Like, so here's the identity we're going to use to help us get started. So here's sine of 180 plus x. What does the right side look like if we use this formula?
Sine of 180 times cos
Sine of 180 times cosine of x. Yep.
plus
Cosine of 180 times sine of x. Yeah. Basically, in this sum, 180 is playing the role of alpha, and x is playing the role of beta. Right? So we're just plugging things in where they go. Now the rest of this, we're almost done. We just have to plug in some values. We just have to, figure out what is sine of 180 and cosine of 180, for which we don't really need a calculator, I don't think. 180 is over on the very left here, right? So what is sine of 180? 0. And what is cosine of 180? -1, yeah. So sine of 180 is 0 times cosine x plus -1 times sine of x. And now we're pretty much done. We just get negative sine x as a result. As desired. That's when I'm feeling too tame for a huzzah. Should we do another? Might as well. All right, another prove. Right, we're going to show that this is true. Okay, well, I guess let's start on the left, mostly because on the left side we have a difference inside a sine, and at least I kind of have an idea of where we could go from there, right? We have a difference formula for the sine function, so I can imagine I could go grab something and replace it, and then we'll just sort of reassess where we're at. So if we use the difference formula for sine, that's this one. So sine alpha cosine beta minus cosine alpha sine beta. We're hoping that it'll just end up being cosine beta minus cosine beta minus cotan alpha. Oh, sorry, cotan beta minus cotan alpha. So I guess one thing we could just observe right here is right now everything in this equation, or sorry, not equation, in the expression, it's all sines and cosines, right? So I want to get to cotan. So it might be good to keep in mind, well, I know that cotan is sine over cosine. That might be a useful observation to make. What's one thing we're allowed to do here? And you know, don't say cancel over addition, because we all know we can't do that.
You could break it into two fractions.
Yeah. Yep, we could break it into two fractions. So we got sine alpha cosine beta over sine alpha sine beta minus cosine alpha sine beta over sine alpha sine beta. Now what? Yeah, now we can whip into a frenzy of canceling, which is always the fun part. So the sine alphas cancel in the first fraction, the sine betas cancel in the second fraction. So we're left with cosine beta over sine beta minus cosine alpha over sine alpha. Now what? Say that again. No, that would actually undo what we just did.
Oh, yeah.
Yeah.
You just transform it into their reciprocal, the cotan.
Yeah, not a reciprocal, but yeah, how they're defined as cotan. And here's one thing that's super important to realize here, especially now in this section on, you know, these are the sum and difference formulas. Eventually we'll look at double angle and half angle formulas. We're getting into territory where we're working with functions where the arguments might be different, like alpha versus beta. So what we want to make sure that we observe, and we're in the clear here, is that it's cosine beta over sine beta. Those are the same. And that's what allows me to say, yes, this is equal to cotan beta. And likewise over here, I've got cosine alpha over sine alpha. Those arguments agree, and that's what allows me to write this as cotan alpha. If it were like cosine beta over sine alpha, I mean, we'd be stuck. There'd be really nothing we could do with that. But that felt like a victory, so I'm going to go back to huzzah. Okay, ready for more? I'll tell you why I love this next one, because I know you're wondering. I love this next one because you look at it and you're like, well, why is this in this section on the sum and difference? Because it doesn't really look like a sum and difference of anything right now. Like we're not adding or subtracting inside the arguments at all. But we're going to fix that real soon. So we want to show that tan of negative x is equal to minus tan of x. And by the way, this property, but we're showing it's not that we can just pull out a negative, right? That's not how it works with trig functions. Tan is a special kind of function, and sine is similar. We say that they're odd functions because they have this symmetry about the origin, because tan of negative x is the negative of tan x, as it turns out. So it doesn't seem like we're subtracting or adding inside, but we are. It is tan negative x is equal to 0 minus x. So that's my first step. I've got a difference inside, and now we can use the difference formula for tan, which is, I'm just copying this from that first page of this section. So now, in the expression we have, alpha is being played by 0 and beta is being played by x. So let's plug stuff in where we go. On top, we have tan 0 minus tan x over 1 plus tan of 0 times tan of x. Now the big question is, what is tangent of 0? It is 0. Tangent, keep in mind, is sine over cosine. So if sine is equal to 0, wherever sine is equal to 0, tangent is equal to 0, and at 0, certainly the y-coordinate there is 0. Clearly that zeroes out, that zeroes out. So we get minus tan x on top, 1 on the bottom, and this is of course just equal to negative tan x. What?
I keep looking at tan x and reading tanks.
Tanks, yep. Let's do one more, you guys, since it's here and everything.
Just one.
Yes, oh yes, yep. I know, I like this one a lot too. Just spend a little bit more time working on it.
Thank you.
Yep.
I just think it's
All right, so another proof. We want to prove the sine of pi over 2 plus x is equal to cosine x. Well, how do we begin?
Use the sine formula.
Yeah, like the sum formula for sine. Yeah, so sine of pi over 2 plus x. What does the sum formula for sine say? Like, how would we write this out, right? So it looks something like this, right? Sine alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. What goes on the other side?
Sine of pi over 2. Cosine of x.
Mm-hmm.
Plus
Plus cosine pi over 2 times sine of x. Yep. And what, what's next here?
Sine of pi over 2 is 1.
Sine of pi over 2 is 1, right? Yeah, pi over 2 is right at the top of the circle here. Sine is 1 there, and cosine is 0. So we're going to need both those values. Sine of pi over 2 is 1 times cosine x, plus cosine of pi over 2 is 0 times sine x. So, of course, this zeroes out, and we're just left with cosine x. Now, not to I swear I'm not bringing this up to pick on Andrew, but if you think about graphing the trig functions, you know how sine and cosine have basically the same shape? They just sort of start at different spots. Yeah? This tells us right here, so another way to write sine of pi over 2 plus x is, of course, to write sine of x plus pi over 2. And I'm just writing it that way because what this is saying is that if we graphed the sine function with a phase shift of pi over 2 units, pi over 2 units to the left, it would be precisely directly overlap the cosine function.
We could have known that like 2 weeks ago.
We could, yeah. But I like to save little Easter eggs for you, right? I'm trying to make the graphing just last as long as possible.